This is Chapter 6, Ionic and Molecular Compounds. We begin with Section 1, Ions and the Transfer of Electrons. If you remember Dalton's theory of the atom, one of the postulates was that atoms can combine together in different whole number ratios to form new substances that we call compounds. And so atoms interact with one another in certain ways that allow them to form these stable configurations. And the stable configurations are the compounds. If they interact by transferring electrons, then ions are formed, and the resulting compound is called an ionic compound. If they interact by sharing electrons, then they form discrete individual new particles, little groups of atoms that are bonded together, and these are called molecular or covalent compounds. The first question you might want to ask about how atoms combine together to form compounds is why they do this, or under what circumstances a few atoms will join together and form this new compound rather than staying as separate atoms. And luckily for those of us who study chemistry, a wide variety of these reactions and configurations can be summarized with what's known as the octet rule. Okay? So to understand the octet rule, go back and think about the noble gases. Remember when we talked about the electron configurations of noble gases, we learned that the noble gases are particularly stable because they have filled energy levels, right? And in particular, they have a filled S and a filled P sublevel in their outermost energy level, the highest N value. So together, this S and P sublevel hold a maximum of 8 electrons. You have 2 electrons in the S orbital, and then the P sublevel is 3 orbitals, which hold 6 electrons. So 6 plus 2 equals 8. So a filled S and P sublevels gives you 8 electrons. We call this an octet. So if an individual atom is stable when it has an octet, it's also true that atoms will interact in ways that allow them both to achieve what looks like or appears to be an octet. And that gives it a stable energy configuration. So the octet rule states that atoms tend to either transfer or share electrons in order to obtain this stable configuration of 8 valence electrons that we call an octet. Here you can see the electron configurations of the first few noble gases so that you can see how they achieve an octet, or how they possess an octet of electrons. Now, the first one, helium, actually doesn't possess an octet. It is an exception to the octet rule because the electrons in helium are in the first energy level, and the first energy level only has an S sublevel. Helium's energy level is filled when it has only 2 electrons, which we call a duet. So this is an exception to the octet rule, and we'll see how this applies to compounds formed from hydrogen as well. But for the others, they do obey the octet rule much better, right? Neon, for instance, has a filled 2s and a filled 2p sublevel. And that gives it 8 electrons in total. Argon has a filled 3s, n equals 3, 3s, and 3p sublevel. Right now, for the n equals 3 energy level, you also have a d sublevel, but if you remember, the d sublevel is actually higher in energy than the next highest energy level, which is n equals 4. And so before we need to worry about the d electrons, we actually have the next noble gas, which is krypton, with a filled 4s sublevel and a filled 4p sublevel. And that also has 8. And if you remember, it does have d electrons, but we don't count d electrons towards the valence shell. So we don't worry about these d electrons. The fact is the d electrons do contribute to the bonding of transition metals in particular and other higher elements, but it's something that's a little bit more complicated and outside the scope of this course. Here we can see a cartoon depicting the 2 different ways that atoms can combine together and interact to form new compounds. On the left-hand side, you have ionic bonds forming, and on the right-hand side, you have a covalent bond forming. So an ionic bond occurs when a metal comes into contact with a nonmetal. Okay? The metal here is M, and the nonmetal is Nm. So a metal, as you recall, has a low ionization energy. It's very easy for a metal to lose electrons and become positive. That's part of what makes it a metal. A nonmetal is the opposite. A nonmetal would prefer to gain electrons to achieve a stable octet, and so it's going to become a negative ion. So if these come together, they can both achieve a stable configuration through the mutual transfer of an electron from the metal to the nonmetal. Okay? And so you end up with the positive metal ion and a negative ion from the nonmetal. And then the positive and the negative are attracted to one another through electrostatic bonding, and so we come up with an ionic bond. Typically in an ionic compound, many millions or billions or trillions of these atoms will interact in this way, and you'll form a bunch of different ions, and they'll come together into a sort of lattice or a network of ions, positive and negative ions. With covalent bonds, on the other hand, you have two nonmetals coming into close contact and interacting with one another. And again, nonmetals don't like to give up their electrons. They have very high electronegativities. It's extremely hard to take an electron off of a nonmetal. And so instead of removing an electron from one or transferring an electron between them, they share the electrons that they have in such a way that it seems that they both have 8 electrons in their valence shell. Okay? So remember, the outermost electron energy level or shell is called the valence shell. And so if you have two atoms that share electrons in their outermost energy level, those electrons, we call them covalent. They are covalent. They belong to both valences or valence shells of the two atoms. And so these shared electrons become a bond that holds the two atoms together. Right? The electrons are drawn to both nuclei from both atoms, and so it brings them together and holds them together. This is what we call a covalent bond. This pair of shared electrons is a covalent bond, and it forms really a new discrete particle, which we call a molecule. Now, keep in mind, this is just showing metals and nonmetals on the one side, and then two nonmetals on the other. Metals and other metals can also interact and form metallic bonds, but that is also something that is outside the scope of this course. So for our purposes, anytime you see a metal involved in bonding or in a reaction, you know that you're going to be creating an ionic bond, an ionic compound. If you only have nonmetals combining together, then you know that you're creating a covalent or molecular compound. For now, we're going to focus on ionic compounds and the formation of ions through the transfer of electrons. So remember, ions form when an atom loses or gains electrons. We don't change the number of protons in the nucleus of an atom in a typical chemical reaction. Only electrons can change. Only electrons can be shared or transferred. So in this case, in order for an atom to become a positive ion, it would have to lose electrons. And in order for an atom to become a negative ion, it would have to gain electrons. In either case, the atom is losing or gaining electrons in order to be left with a stable octet, an electron configuration identical to the nearest noble gas. Okay? And so since metals are large and have low ionization energies, they tend to form positive ions. We call these cations. And nonmetals have high ionization energies. They're small, and they tend to form negative ions, which we call anions. Again, an atom is trying to complete an octet. So in the case of metals, we have a noble gas core, right? In this chart, you can see the electron configurations of the first few metals in group 1 of the periodic table, group 1A or 1 in the new counting system. And so each of these is a noble gas core, represented by this bracketed symbol here, with one additional electron tacked onto its outside, onto the valence shell, what we call the valence shell, right, the highest energy level. So in order to achieve a configuration like a noble gas, the easiest thing that these atoms can do is just simply lose this electron in the outermost shell. And so if you have a neutral atom, a charge 0 atom, and it loses an electron, which has a negative charge, then you're going to be left with an ion that has a +1 charge. And so all of these atoms, all of these elements in group 1, the first column of the periodic table, tend to form +1 ions. Okay? And that gives them the configuration that is just like their noble gas core. Okay? So we can see that the charge on the ion comes directly from knowing how many valence electrons the atom has. And the number of valence electrons that the atom has can be seen by looking at its position on the periodic table. So this is going to be a common theme. We'll see it as we go through the next few groups of the periodic table as well, that we can tell what kind of ion an element will form based on its position in the periodic table. Here we can see the group 2A, or 2 elements, beryllium, magnesium, calcium, strontium. And again, each of these has this core, this set of core electrons that has the same configuration as a noble gas. helium, neon, argon, krypton. And this time they each have 2 additional electrons in their valence shell, in their outermost energy level. Okay? The S shell for each of these is filled. So we have 2s2, 3s2, 4s2, 5s2. And so each of these elements is going to lose both of those electrons in order to achieve the noble gas configuration. And again, if you lose 2 electrons, now you end up with a +2 charge. And so the elements in group 2 of the periodic table tend to form +2 ions. Going across the transition elements to the p block on the right-hand side of the table, we get to group 3a, or group 3. And there's only a couple of metals that we really need to worry about in this group, and these are aluminum and gallium. The other element in this group is B, which is boron, which is a nonmetal. And so that is not going to form ions. We'll learn about that more when we get to covalent compounds. Okay? So the aluminum configuration is like neon with 3 additional electrons. 2 electrons in the 3s sublevel and 1 electron in the 3p sublevel. Gallium is similar. It's like argon, but with 3 electrons in the n equals 4 energy level. Now, gallium also has, again, these 3d10 electrons, but we're not going to worry so much about these. They are not considered part of the valence shell. Okay? So when gallium loses electrons, it loses electrons in the valence shell in the n equals 4 energy level. So it'll lose these 2 electrons in the 4s sublevel and this electron in the 4p sublevel. And so instead of being left with strictly an argon core, it's going to be left with an argon plus a filled 3d sublevel. But again, this is just a sort of a complication. It doesn't really change much. You're still losing 3 electrons here, and so you're forming a +3 ion. For aluminum, it's much more straightforward. We don't have to worry about those d electrons yet. All you need to know is that you lose all 3 electrons in the n equals 3 energy level to become aluminum 3+. So again, group 3 +3 charge. Okay? Your group 3 means you have 3 valence electrons. When you lose 3 valence electrons, you gain a +3 charge. Sometimes students wonder whether an atom, a metal in particular, will lose one or some of its valence electrons, but you have to remember that it's trying to achieve that noble gas core. So it's going to shed as many valence electrons as it can to get down to the stable filled octet in the center. Okay? So in this case, it loses all 3. But what does it actually look like when a neutral atom, neutral metal atom in particular, loses an electron to become a positive ion? Well, we can't really see an individual atom. What it means to see something visually with your eye doesn't really even make sense so much at the atomic scale. But we can still measure properties of individual atoms through sort of complicated experiments, and so we can find what the radius is for an atom or what the radius is for an ion. Okay? And what we find is that when a neutral atom loses an electron, as you might expect, it gets a little bit smaller. In general, you're taking all of the electrons out of the outermost energy level. Okay? And the outermost energy level is the highest energy level. It's the one furthest from the nucleus. So if you remove all of those electrons, you're left with energy levels that are much closer to the nucleus. And so the size decreases. So for all of the metals, the positive ions that they form are smaller. They have a smaller atomic radius than the neutral metal atoms. Here you see this for sodium, where it loses this 1 valence electron in the outermost n equals 3 energy level to become like neon, and you end up with a smaller +1 ion. Here you see the same thing, but for magnesium. In this case, it loses 2 electrons to become like neon, right? It still ends up like neon with a filled n equals 2, 2s and 2p sublevels, but it's lost 2 valence electrons to do that, and so it becomes 2+. And so the magnesium 2+ is smaller than the neutral magnesium atom. Nonmetals, on the other hand, do not lose electrons. They gain electrons. And so by gaining electrons, they become negative ions, anions. And the reason they gain electrons, again, is they're still trying to achieve an octet, but now they're just a few electrons short of getting that 8 filled octet, and so it's easier for them to just gain 1 or 2 or 3 electrons to become an ion, rather than lose 5 or 6 or 7 electrons. So if we skip all the way to the other side of the periodic table in group 7A or 17 in the new system, this is right before the noble gas group, right? We're not worried about the noble gas group because they don't form ions. They're already stable. They don't need to shuffle around their electrons to get an octet. They already have an octet. That's the point. So group 7A is the last group before the noble gases, which means they are all 1 electron short of an octet. They all have 7 valence electrons in their outermost energy level. So fluorine, for instance, has 2 electrons in the 2s orbital and 5 electrons in the 2p orbitals. That's a total of 7 valence electrons. If fluorine wants to have 8 valence electrons, all it needs to do is gain 1 more electron, and it becomes F-. And that gives it a noble gas configuration, not like helium, which was originally its core, but now it's completed sort of a new shell, and so now it has a configuration similar to the next noble gas in this case, which is neon. Okay? Same thing for chlorine. It has 7 valence electrons in the n equals 3 energy level. We don't need to worry about d orbitals yet. And so chlorine gains 1 to become Cl-, and that gives it a configuration like argon. Bromine and iodine both have d orbitals, d electrons that are filled, but this still doesn't really change matters. In fact, even when it gets that 1 extra electron, now it really has a configuration just like krypton. We don't even need to say that it has additional d electrons because krypton naturally has those d electrons. And so again, each of these elements in group 7 is just gaining 1 electron to get an octet, and so they each form a -1 ion. The group right before that is group 6A or 16. These each have 6 valence electrons, 2 in the 2s, 4 in the 2p for oxygen, right? For sulfur, it's 2 in the 3s and 4 in the 3p. For selenium, 2 in the 4s and 4 in the 4p sublevel. It also has the 3d electrons, but again, we're not too worried about those. So if you have 6 electrons and you want to get 8 electrons, you gain 2 electrons and you become O2- or S2- or Se2-, right? And this gives them their noble gas configuration. And then the last ions that we really need to worry about for now are nitrogen and phosphorus, and those are in group 5A or 15, and these all have 5 valence electrons. And so rather than lose 5 valence electrons to become a +5 ion, which would be very unstable, they gain 3 electrons to get an octet, and that makes them a -3 ion. Okay? Looking at the picture of what happens to the atom, again, we can see that when a neutral atom gains new electrons, it's going to increase in size. Right? Now, even though the new electrons are not going into a higher energy level, right? In this case, they're going into that 3p sublevel and completing it. But even so, putting another electron into that energy level, electrons tend to repel themselves, and it will sort of inflate the electron cloud a little bit as they sort of try to get away from one another. So it will still increase the size of the atom, okay? Which is what you would expect, right? If you add an electron to an atom, to the outside of an atom, it's going to get a little bit bigger. Here we can see the names of the ions, right? So we've talked about how the main group elements form ions, what charge they have because of the loss or the gain of electrons. But there is also a standard for assigning names to these ions. And it's pretty simple. For the metal ions in particular, it's very simple because we just keep the name of the metal. Okay, so all of the metal ions have the same exact name as the element that they came from. Lithium becomes the lithium ion, sodium becomes a sodium ion, etc. For the nonmetals, it's a little bit more difficult, but you just take the first syllable from the element name, and then you add IDE to the end. So nitrogen becomes nitride, phosphorus becomes phosphide, oxygen becomes oxide, then you have sulfide, fluoride, chloride, bromide, iodide. Okay, so the IDE ending is tacked on to nonmetals, the name of a nonmetal, to make the negative anion. This chart shows you, again, those metals with their charges based on their group. We're going to see the sort of explicit mathematical way to calculate the charge based on the group, but I don't expect you to take this table too seriously. It does show the accurate group numbers, but it's putting all of the ions on the same row as the noble gas configuration they have. So for instance, this row here, sodium, magnesium, and aluminum are not actually in the same row of the periodic table as nitrogen, oxygen, and fluorine. So this is sort of a shuffled and condensed version of the periodic table, and in my opinion, it's not actually that helpful for remembering the ions, because you can just do it by looking at the periodic table, which is what we're going to do now. Okay. One thing to remember when you do this is to try to use the old group numbering system if it's available to you, or if you can remember it. That's the one with the A. Obviously, you just drop the A, and then you can get the charge directly from the group number. If you use the new numbering system, you just have to remember that for group 13 through 17, you need to subtract 10 from the group number in order to figure out the number of valence electrons, and therefore how many electrons need to be gained or lost. Okay, so just keep that in mind when you're dealing with the group numbers for the elements. So we begin with the metals, right? Again, metals are losing all of their valence electrons to become positive ions. That means if you know how many valence electrons a metal has, you automatically know the charge, because it'll be equal to the number of electrons that it lost. And since the number of valence electrons is just from the group number, then it's a very, very simple relationship. The charge that a metal ion forms is equal to its group number. Okay? The only exception here is aluminum. In the new system, if you're looking at aluminum, you just have to subtract 10 from that, like we discussed. But other than that, the charge on a metal, a main group metal, is the same as its group number. When we get to the transition metals, it's going to be a little more complicated. They can form multiple ions. But for now, just focus on these that you see here. For a nonmetal, it's slightly more complicated, but not really. There's two ways you can do it. You can either figure out how many valence electrons it has from its group number, and then count up to 8. Right? So if an atom has 5 valence electrons, you count up 6, 7, 8, and you get 3 additional electrons to get an octet, and that gives you a -3 charge. If it's a group number of 6, it has 6 valence electrons, you need 2 more to get to 8. If it has 7 valence electrons, then you just need 1 more to get to 8. Okay? Right, another quick way to do that is to just take the group number and subtract 8, and that'll give you the charge with the correct minus sign, because these are all gaining electrons, and so these are going to get a negative charge. So if your group number is 7, 7 minus 8 gives you a -1 charge. If your group number is 6, 6 minus 8 gives you a -2 charge. If your group number is 5, 5 minus 8 gives you a -3 charge. Okay, so that would be a more formal way to do it, but usually in practice you can do it just by counting up from the number of valence electrons. So, how do we use this to write the symbol for a particular ion? Well, if we have an ion with 16 protons and 18 electrons, what are we looking at? Right? First, we need to know what element it is. The element that it is determined by the number of protons, which is the atomic number. Right? So if it has 16 protons, then the atomic number equals 16. And the element with atomic number 16, if you look it up in the periodic table, is sulfur. Okay? And sulfur has the symbol S. Now we just need to know what charge is on this ion. And if you remember back to previous slides, when we talked about protons and electrons and atomic structure, the charge is just the number of protons minus the number of electrons. And so the charge in this case is 16 minus 18, which is -2. Right? And so we have a 2- ion. This is the symbol for the ion. This is called sulfide. We take the initial syllable from sulfur and we add the ending IDE to make it sulfide. Okay? Again, this is explicitly telling you the number of protons and electrons, and it's telling you all of the electrons, not just the valence electrons, so don't get confused. If we're looking at just the valence electrons, well, sulfur has 6 valence electrons because it's in group 6A. And so sulfur needs 2 more electrons to get an octet, and that's why sulfur has a -2 charge. Here they're just explicitly telling you the protons and electrons, so it's actually a little bit easier than that. The second one, we have write the symbol for the ion with 12 protons and 10 electrons. So again, the atomic number in this case is the number of protons, which is 12. And so that is magnesium. Okay. Magnesium has the symbol Mg. Okay. The charge on this magnesium ion, which 12 protons and 10 electrons, remember a neutral atom of magnesium will have 12 protons and 12 electrons. They'll be equal. This one has 2 fewer electrons, and so you can probably guess that it has a +2 charge. If we do that formally, then the number of protons minus the number of electrons equals 12 minus 10, and you're left with +2. Right? I'm explicitly writing the +2 to indicate that this is an electrical charge we're talking about. So this magnesium ion has a 2+ charge. Okay? And this, the name of the ion, is the same as the name of the element, right? We can just sometimes call it the magnesium ion if we want to specify what we're talking about. Okay? And again, this is because magnesium is in group 2A. It has 2 valence electrons, and so those are the 2 valence electrons that it lost, so that it now only has 10 electrons. And here are those answers again. Now consider the elements calcium and chlorine. We want to figure out what kind of ions calcium and chlorine makes without having any other information given to us, without knowing the number of protons or the number of electrons or any of that stuff, right? But we do know what the elements are. We know that calcium is Ca and chlorine is Cl. So if we have access to a periodic table, we can look for these element symbols, right? And so if you look, Ca is all the way on the left-hand side in group 2. Okay? That means that calcium is a metal, because it's all the way on the left-hand side. Chlorine is all the way on the right-hand side in group 7A or 17. And so chlorine is a nonmetal. Again, you should be able to tell that just from their positions on the periodic table without looking up anything else. You should also be able to tell from the position on the periodic table how many valence electrons they have. Calcium, like I said, is in group 2A, so it has 2 valence electrons. I'm just going to write it has 2 electrons here. We're going to understand that this means valence electrons. It actually has, a neutral atom of calcium actually has 20 electrons, but 18 of them are part of the noble gas core, and only the 2 outermost electrons are the valence electrons. Okay. Chlorine is in group 7, and so chlorine has 7 valence electrons. Actually, chlorine has 17 valence electrons, right? But again, 10 of those are the noble gas core, which is like neon, and the outermost shell is 7 electrons, and that's the valence electrons. So in order for these to form ions, we need to think about how these gain or lose electrons. Okay? State the number of electrons that must be lost or gained for each to acquire an octet. That's question C, right? Calcium has 2 electrons, so it's pretty easy for calcium to lose 2 electrons rather than to gain 6 more. So calcium is going to lose 2. Right? It has 2 valence electrons, it'll lose both valence electrons. And that should also make sense to you because calcium is a metal, and metals tend to lose their electrons and become positive. Chlorine is a nonmetal, and they tend to gain electrons, right? 7 is just 1 electron short of having a full octet. So chlorine will gain 1 electron. And so now that we know how many electrons are lost or gained, we can clearly write the symbol. Calcium loses 2 electrons, and so it gains a +2 charge, right? Calcium loses 2 electrons, and so it's left with a +2 charge. Chlorine gains an electron, and so it's given a -1 charge. And we just write it like this. We don't need to put the 1, Cl minus, as a superscript. And so these are the symbols of the ions that are formed. What are the names? Well, Ca2+ is just the calcium ion. It's the same name as the element. Chlorine, though, we take the first syllable, chlor, and instead of the -ine ending, we change the ending to -ide. And so this becomes the chloride ion.